So, hi guys. So you know my son. I've had him film for me a couple times. Um, he thinks it's funny that I stand in a bathtub and talk to you. But his name's Connor, which I think he probably caught already. But um, he and I were talking the other day, and he was a little confused, and he asked me a question. He says, "What rhymes with orange?" And I looked at him and said, "No, it doesn't." You get it? What rhymes with orange? No, no, it doesn't. So um, he had another question for me after that, though. He said, "Dad, can you explain what a solar eclipse to me is to me? Can you explain what a solar eclipse is?" And I looked at him and said, "No, son." Dad jokes. All right. Anyway, I'm supposed to be doing something here. We are what? We're looking at another example problem with electromagnetic induction. Specifically, this one uses the idea of putting that metal rod that I introduced a couple videos ago. That's moving in a magnetic field. We put that metal rod onto a set of conducting rails. And then what are we doing? We're sliding it to the right. So somebody has to actually, well, in this case, somebody's hand is on it and moving it physically to the right. We could have this, I don't know, some other power source moving it to the right somehow or something. This is a little contrived, but that's okay. So we've got somebody moving this metal rod to the right. And as a result of that, just like we mentioned a couple of lectures ago, a couple videos ago, we get a separation of our charge in our metal rod. Let's see here. There we go. So we get a positive side and a negative side. There we go. We get a positive side and a negative side. And as a result, we've got, let's see, conducting rails here. Those conducting rails act like a pathway for my current to run from positive to negative across my battery or from my battery. And of course, if I've got current going around this way, we've got to have a complete loop. So that means that my current has to run upwards through that metal rod. All right. Now, our goal in this particular problem is to find the current in this circuit. So we've got a little light bulb there. Our light bulb acts like a resistor. It says it has a resistance of 96 ohms. And our goal is to find the current that's running not only through the light bulb, but through all parts of this circuit. Remember that if we've got a series circuit where there's only one pathway, that the same current has to run all the way around that circuit. So if I've got, I don't know, 2 amps of current through the light bulb, then I've got to have 2 amps of current through that conducting rail as well. And also the metal rod, that vertical metal rod that's sliding to the right. Okay, so there's my goal. And I've got some relevant information here, but let's give ourselves a little bit of room to write on. Oops, oops, oops. What am I doing? Oh, I'm making mess. Okay. All right. So let's redraw our problem a little bit, and I am going to just act like well, that's the worst resistor I've ever drawn, probably. I've got a resistance there of what, 96 ohms. We'll just call that R. I've got that metal rod. That metal rod is going to the right. I have a magnetic field that's into the screen. What else do I have? If I go back to that last page, I had the length of that metal rod. Let's see here. It said that the length was 1.6 meters. We were given the value of the magnetic field. The magnetic field is 0.8 Tesla. The resistance was what, 96 ohms. Let's see, the speed of the rod said it was moving at a constant rate to the right at 5 meters per second. All right, so that's the information that I have. And I've got to think about the tool that I have to answer this question. Well, and what was the question? The question was, what's the current that's running through this circuit, through the light bulb? Okay, so I've got some kind of current running through here, something like that. And we're asked what that current is. How are we going to solve for that? Well, you guys may recall Ohm's law. I hope you recall Ohm's law. That was the chapter with all the circuits on it and so on and so forth. Ohm's law said that voltage is equal to current times resistance. Now, we've recast this term for voltage. Now, we're not using voltage anymore, at least, I mean, we can, it's fine, but we're also calling it EMF. So EMF is equal to current times resistance. So if I knew what my EMF was, well, I've got the resistance, I could figure out the current. All right, awesome. So I need to figure out what that EMF is. And I'm going to erase some things. There we go. Maybe it would work better if I did. Okay, probably erased too much. That's all right. Dot. All right. So I need to figure out what the EMF is, because if I knew the EMF, I'd be all set. Why are you not going to black? What's your problem? Oh, there we go. Well, the only tool I have to figure out EMF is this one here. EMF is equal to N times change in flux over change in time. Let's see, how many loops do I have? I've got one. Yeah, this thing's not wrapped around a whole bunch of times or anything like that. So N is one. N is one. Worst one ever. There we go. So N is one. So let's see. All I need to do then is, well, let's see. Recall what flux is. Flux is BA cosine phi. All right. Well, so the area that I'm thinking about is what? It's basically that right there. It looks a lot like a rectangle. Okay, it looks a lot like a rectangle. Now that what's the angle between normal to that rectangle and the magnetic field? Well, they're both basically, I don't know, either into or out of the page. I guess it's into the page. Okay, so it's either 0 degrees or 180 degrees, one or the other. Either way, it doesn't matter, because it's going to either give us 1 or -1 when we stick it in the cosine. Cosine of 0 is 1, cosine of 180 is -1. And it's just magnitudes that I'm worried about here. So not really going to let that concern me a whole lot, which it is. So phi is 0 degrees, cosine of 0 is 1. So this gives me that my flux is what? B times A. All right. Do I have the magnetic field? Yes, I do. It's 0.8 Tesla. Do I know what the area of a rectangle is? Yes, I do. Area is equal to what? Width times length. Do I have the length? L. Yeah, it's 1.6 meters. Do I have the width? No, I don't. There's my width right there. Let's call this X. So that's X. So area now is going to be equal to what? Area is equal to X times length. All right. So that means that my flux is equal to B times X times length. All right. Now, let's plug that flux into my EMF equation. So it looks like EMF now is, well, N was 1. times change in B times X times L over delta T. All right, now, is the magnetic field changing? No, it's 0.8 Tesla. Is the length changing? No, it's 1.6 meters. Is X changing? Well, yeah, as I slide this bar to the right, my width is changing. Yeah, it is. But the magnetic field and the length aren't. So what I can do is I can pull them outside that delta because they're not changing. That delta says change in BXL. Well, if B and L aren't changing, I can pull them outside of that. So let's do that. This is equal to 1 times BL delta X over delta T. Delta X over delta T. Change in distance over change in time. What is that? Change in distance over change in time is speed. All right. I've got a bit of a mess. I need some space, but I need to keep in mind that that delta X over delta T is speed. And I'm going to erase this, and we're going to kind of redraw. All right. So EMF is equal to what? B times L times delta X over delta T. This was B times L times V. And we have all that. B is 0.8 Tesla. L is 1.6 meters. V is 5 meters per second. And when we plug all that in, we get 0.64 volts as a result. That's awesome. That's my EMF, 0.64 volts. Okay, and then current is what? It's EMF over resistance. It's voltage over resistance, 0.64 volts over 96 ohms. And when I plug this into a calculator, I get out 0.067 amps. And that is my current through the light bulb. And as we saw in the video, we actually can have a changing magnetic field generate light in a light bulb. You saw the Nat Geo video now is what I'm talking about. The demonstrator dropped that that magnet through that middle pipe, and we saw the lights light up as the magnet passed near them. Same idea here. So current is 0.067 amps. That answers our question. Okay. Oops, still coloring on that. So what's next? Okay, is there anything else to consider in this setup? What else could we figure out? So we've got current and we've got voltage. Maybe we might be interested in the rate at which energy is being used, or the rate at which we've got to supply energy to move this rod to the right. So calculate the rate at which energy is used. You guys remember what that is? The rate at which energy is used? That's power. Power is energy over time. So when I ask this question, I'm literally asking, what is the power? Well, power is what? It's current times voltage. And we have that, of course, we're calling voltage EMF. That's fine. This is 0.067 amps times 6.4 volts. And when we do the math here, we get that the power is 0.43 watts. So we've got to supply 0.43 watts of power to keep this current going. So 0.43 joules per second we've got to provide to make this rod slide to the right. All right. Which honestly, this is kind of a little bit of a contrived problem. Imagine putting your hand on a rod and moving it at 5 meters per second. That's pretty fast. Usain Bolt runs at about 10 meters per second. So, all right, okay, that's fine. All right, so there's our power. Anything else we could consider? Yeah, well, okay, let's figure out what force we actually have to exert to keep this rod moving. Well, let's see, how are we going to do that? The force. Let's see, if I think about force, I think about all the stuff that we did last semester in 111 with forces. And I think about a free body diagram. Okay, so if I think about this rod there, I've got a force there that my hand's exerting, pushing this thing to the right. Would there be any other forces acting on this metal rod? Well, there's got to be something, surely, because right now the force is unbalanced, and we said that the velocity is constant. So there's got to be something. Let's think here. Let me move my hands away from my mouth. We've got current running through this rod. That current is in a magnetic field. If I've got a current in a magnetic field, there's going to be a force on whatever's carrying that current. F is equal to ILB. Force due to magnetic field is current times length times magnetic field times cosine phi, I should say. So let's remind ourselves that F due to a magnetic field on a current carrying wire or current carrying rod or whatever is F is equal to ILB cosine of, I don't know, some angle. Maybe I should not use phi. I don't remember what the angle was that we called it, but maybe I'll just use something other than phi right now. So what other angles do we know? Theta, whatever. Okay, so what is the direction of that magnetic field? Well, first off, the current's upwards towards the top of the page. Magnetic field is into the page. As a result, looks like that angle between them is 90 degrees. F is equal to ILB cosine sine theta. Yeah. Guess what? I'm not erasing that, or I'm not redoing this. There we go. You guys hollering at me, screaming at me. Dr. Houston, fix it. You're wrong. There we go. I fixed it. F is equal to ILB sine theta. Excuse me. I forgot because why? Because that's going to drop out. Sine theta is going to be 1 because the angle is 90 degrees between between the current going upwards and the magnetic field pointing into the page. There we go. Theta is 90 degrees. And sine of theta or sine of 90 degrees is 1. All right. So we get that the force due to the magnetic field is ILB. There we go. What's the direction of that force? You've got to use the right-hand rule. Current is going upwards. Magnetic field is pointing into the page. Basically, magnetic field is pointing away from me. The palm of my hand should be towards the screen of the computer. Okay, yeah, good. Looks like the force is to the left. So the force due to this magnetic field is to the left. Well, let's see, if I've got a free body diagram, then the sum of the forces is going to be mass times acceleration, Newton's second law. Acceleration is 0 because the velocity is constant. There we go. That means that my forces have to balance. So the force that my hand exerts is got to be equal to the force due to the magnetic field. Well, I know what the force due to the magnetic field is. It's ILB. All right, so that means that my force is equal to 0.067 amps times 1.6 meters times my magnetic field of 0.8 Tesla. It looks like my force is 0.086 newtons, and that is the result there. All right, sorry about stumbling through the sine, cosine thing. All right. So in order to keep this thing moving at a constant rate, I've got to supply 86 millinewtons of force to the right, just to compensate for the force due to the magnetic field that's pushing to the left, that's resisting the motion. And that's what this slide says. All right, one last slide before I put an end to this one. I know the video's kind of long. What's a practical application of magnetic induction? Well, you're staring at it right now, induction stoves. Why are induction stoves nice? If you guys, any of you have had one of these, you'll know that you can actually put your hand on the surface of the stove and it will not get burnt. Even when the burner, so to speak, is on, even when the stove is on, you can place your hand directly over where you would place a pot, directly on where you would place a pot, and your hand will, I mean, it might be a little bit warm. I don't know quite, but it definitely won't get burnt. In a perfect world, it wouldn't get warm at all. It may not get warm at all. I don't have an induction stove. I need to go check these things out, I guess. Yeah, this is a nice safety feature, especially for parents of young children. So you can put your hand on there; it doesn't get burnt. But how is it that it actually will heat up a pot? Well, in the surface of, or underneath the surface of that induction stove, there's coil of wire, and that coil of wire, when we turn the stove on, ends up having, of course, current running through it. Okay. And current running through it, actually, it's constantly flipping back and forth. Directions, I would imagine, are constantly changing in some way. All right, so we've got a current that's constantly changing directions. And then above that, we put what? We put a metal pot. Well, if we've got a current that's constantly changing directions, there, it's going to end up generating a magnetic field that's constantly changing directions. We've got a magnetic field going up through the pot, magnetic field going down through the pot. We've got a changing magnetic field there in the region of space where we have a conductor. If we have a changing magnetic field, then we've got a change in flux. If we've got a change in flux, then we've got an induced voltage, an induced EMF. If we've got an induced voltage, we've got an induced current. What does the current travel through? The current travels through this metal pot. What happens when you've got current traveling through metal? What happens when you've got a lot of current traveling through metal? You guys experienced this when we tried to get you to light up the battery or the bulb, when we had one wire, one battery, one bulb, and maybe you had a little short circuit, and what happened? The wire got really stinking hot, right? That's exactly what happens with that metal pot. When we've got a change in flux, we have a induced voltage. When we've got an induced voltage, we've got current running around the pot. When we've got current running through metal, the metal gets hot, and then we got nice boiling water. Of course, why won't this work on a glass pot? Because, well, a glass pot will not conduct electricity well at all, so no current through it. So as a result, we don't have the electrons colliding into the things, into the atoms in the pot and setting them vibrating, which is what's going on in the metal pots. So we don't end up with heat as a result. So this is why if you've got an induction stove, you have to stick with metal pots. A glass pot will not work on that. And this is exactly how an induction stove actually works. So pretty cool. All right, I've talked more than enough. Voice is going hoarse. Horse is going voice. Don't know what that is.